screen visible? Hello? Was my screen visible, Nagendra? Welcome to the live interactive session number 9 of the subject Mechanics of Fiber Reinforced Polymer Composite Structures. I'm going to discuss some sample problems which will be useful for solving assignment number 10. Let's start. So the first question is, a thin cylindrical pressure vessel is originally made of aluminium having density 2700 kg per meter cube and sigma y equal to 250 megapascal, which is the yield point stress. Now the cylinder has an internal diameter of 1 meter and it should be able to withstand an internal pressure of 1 megapascal. Now in order to reduce the weight, the cylindrical pressure vessel having the same radius now needs to be made from unidirectional carbon epoxy laminae with laminar thickness 0.25 mm and having a stocking sequence of 092s. That is 090 symmetric 2 times. Now the properties of the unidirectional carbon epoxy lamina are given, which includes its engineering constraints and the ultimate tensile and compressive strengths in longitudinal and axial direction, in axial and transverse direction. Now the first question is, to neglecting residual stresses due to manufacturing, the minimum thickness of the cylinder made from aluminium has to be found by using the maximum shear stress theory. So now we are considering a thin cylindrical pressure vessel. So first thing will be to find its stresses. So there are two types of stresses will be applied on it, the hoop stress and the longitudinal stress. The formula of hoop stress is pressure into diameter divided by 2 into the thickness. Thickness is not known to us, so we will find the hoop stress in terms of H, that is the thickness of the thin pressure vessel that we need to find. Next is the longitudinal stress, which is equal to P pressure into diameter divided by 4 into the thickness. Again, we will get the value in terms of unknown variable, that is thickness. Now the principal stress, this is the formula of the principal stress, sigma 1 and 2 that you can find. We already know this equation. Now comes the maximum shear stress theory. So according to the maximum shear stress theory, a material will fail or yield when its maximum shear stress equals or exceeds the shear stress value at the yielding point in the uniaxial tensile test. So already in the question, the shear stress value at the yield point is given, that is 250 megapascal. So in maximum shear stress theory, we are getting three types of stresses in three directional principal stresses in direction 1, 2 and 3, and according to their values in increasing order, we take the values of the maximum and the minimum principal stresses in the directions and we compare it with the shear stress value at the yield point. So here the principal stresses in direction 1 is the highest, which will be the hoop stress, whereas in direction 3 it will be 0. So this is the maximum and the minimum value of stresses, so we will consider those. So we will get this get this formula from the maximum shear stress theory, that sigma 1 minus sigma 3 divided by 2 will have to be equal to the shear stress value at yield point divided by 2. So from this equation we can get the minimum thickness, that is required to construct the cylinder so that it can withstand the pressure. So that we will get the value as 2 mm here. Next question for the same given data is asking, when the cylinder is made of 092s carbon epoxy, then what will be the percentage reduction in overall weight compared to the cylinder made from aluminium? So we have to compute the weight. So the formula of weight we can find, we are already given the density and we need the volume, and then from that we can compare the weight. So So weight will be equal to density into the volume. Now the area of both the cylindrical vessels will be same, only the thickness will vary because of the thickness which you get from the aluminium cylindrical pressure vessel and the thickness of the composite pressure vessel. So only comparable thing here is the thickness and the density. So by the formula of percentage reduction in overall weight, the weight of the aluminium minus weight of carbon epoxy divided by weight of the aluminium. Now area will be same, so only thing will be density and thickness. So density into area into thickness is the formula for weight. So area getting cancelled. So thickness here 092s, that means 0 and 92 laminas in symmetry will become 4 and 2s means it is double, that means 8. Now the thickness of one lamina is 0.25 mm, so multiply by 8 we will get the thickness as 2 mm. And also from the previous question here the thickness we are getting for the aluminium cylindrical vessel also 2 mm. So the thickness is also same, the only thing different is density. We will put the value in this formula and we can get the percentage reduction in the overall weight. Next question with the same data. They are asking when the pressure vessel made from 092s carbon epoxy is subjected to an internal pressure of 1 megapascal, then the global strains induced at the top 0-degree ply are. So we have to find the global strains induced. To find the global strain, we have to find, so the first step will be to find the Q matrix of all the laminas. So to find the stiffness matrix, reduced stiffness matrix of the laminas, the engineering constraints are already given in the question. So we will get the Q matrix. Then for every 0 and 90-degree lamina, we can convert it in. We can get the Q bar matrix of all the laminas. Next comes we have to find for the whole laminate. We have to find the global strain of the whole laminate. For finding the whole laminate, we have to consider the ABBD matrix. Now here it is a symmetric. It is symmetric. That's why there will be no B matrix. Also there is no curvature in this composite. Hence there will not be any D matrix also. So the only matrix that we have to consider here will be the A matrix. Now the formula of A matrix we know. Only we need is the thickness of each lamina and the reduced stiffness matrix of that lamina, and we have to multiply them and do the summation of for all the laminates to find the A matrix of the whole laminate. So from that formula we can get the A matrix. Now A matrix is n equal to A into the mid plane strain. So n value we are n values are the hoop and the longitudinal stresses that we already found in the first question. So here in the previous question we got the stresses and these are load. Therefore they will be multiplied with the thickness and then we will get the value of the load, that is nx and ny, and nxy is equal to 0. Now to find the mid plane strain, the equation is mid plane strain equal to inverse of the A matrix and the loads. So the load values are given. A matrix we already found. We have to find the inverse of the A matrix and multiplying them we can get the mid plane strains. Now to now using the strain displacement equation, there is no curvature. Because of that, the global strains will be equal to the mid plane strains. Hence, the value for the global strain at the top 0-degree ply will be equal to the mid plane strains that we can find here. Then next question, for the same data is that when the pressure vessel made from 092s carbon epoxy is subjected to an internal pressure of 1 megapascal, the material axis stresses induced in the 90-degree plies are. So in the previous question, they found the global strain, the mid-plane strains and the global strains. So we got the global strain for 0-degree ply. So now we need to find the global strain of the 90-degree ply, which you can do by using the transforming matrix. You can find the global material axis strains in 90-degree ply from the global axis. After that, you got the strain by using the stiffness matrix of a 90-degree ply. You can convert the strain to stress, and from that equation, you can find the value of the material axis stresses in the 90-degree plies. Next question is, using the maximum stress criteria, the factor of safety of the pressure vessel made from 092 as carbon epoxy lamina and subjected to an internal pressure of 1 megapascal is. So for that we have to make the failure index table. That is, we have to find the stresses, the principal axis stresses of 0 degree angle lamina and the 90-degree angle lamina.
అడుగుతుంది ఉన్నారా లేదా అని.
Can you mute the mic, Nagin?
మేడం
Mute your mic, please.
ఓకే ఓకే.
Thank you. So here we need to find the failure index table for each ply. There are only two angles are used, 0 and 90. So even though they are in symmetry, only 0 and 90 angle ply laminates we need to consider, and we have to find the principal axis stresses sigma 1, sigma 2 and the tau 1, 2. So after finding the values of sigma 1 and sigma 2, as we did in the last question, we have to, like here we did the material axis stresses of 90-degree plus. Similarly, we have to do for 0-degree, and we will get these values. After that, we have to find the stress ratio. To find the stress ratio in the first 0 angle, sigma 1 is given, which is in a longitudinal direction. So sigma 1 ultimate we have to find from the given data, that is here is 2400 megapascal. So stress ratio we can find, we have to divide this with 2400 megapascal and we will get a value. Similarly, sigma 2 value is given here 50 megapascal. So we will divide sigma 2 value of ply 1 with 50 megapascal and we will get the stress ratio number 2, and stress ratio number 3 is 0 as tau 1 2 is 0. Here there is no negative value, so there is no compressive ultimate stress there. So we will only consider the ultimate tensile stresses in 1 and 2 direction. So when we compare the stress ratios, we consider the value which is highest, which means this ply in this direction is the first one to get failure. So from that value, we can get the factor of safety by taking the inverse of that value, which is here 0.74162. We take inverse of it and we will get the factor of safety. It's visible, I think, now. So I will repeat it. So we, in the last question, we found the material axis stresses in 90-degree ply. Similarly, for 0-degree ply, we can get. And then we have to find the stress ratio by dividing this with the ultimate tensile stresses. As there are no negative values, so there won't be any compressive stresses. So in this principal axis, we will divide them with the ultimate tensile stresses and we'll get the stress ratios. Now we will compare the one which is the maximum and almost close to 1, which means that ply in that direction is the most tendency to fail. From that, we can get the factor of safety as the inverse of that value. Okay. Now next question. A thin cylindrical pressure vessel with an internal diameter of 1 meter is made of 0.25 mm thick graphite epoxy plies having a stocking sequence of 0, 45, minus 45, 90 symmetry and needs to withstand an internal pressure of 0.5 megapascal and a twisting moment of 157 kilonewton meter. The reduced transformed stiffness matrices for the plies are given. So they are asking the global axis strains in the 0-degree plies. So in this question again there is a thin cylindrical pressure vessel. So here in x and y direction you can see when we consider the x direction it is the longitudinal stress, whereas in y direction it is the hoop stress. So sigma in x and y direction is such that sigma x in this direction is the longitudinal stress which is PD by 4h, whereas sigma y is the in the hoop direction which is PD by 2h. This is the formula to find the stresses in hoop and longitudinal direction. Now again here to find the global axis strain, first thing will be to find the A matrix. As it is symmetric, there won't be a B matrix and there is no curvature and moment curvature here. That's why there won't be any. We will not consider the D matrix. So only the stresses are given here in x and y direction and tau xy is given. As there is in the question it is given that twisting moment is given. So from that value we can get the tau xy. So the formula of tau xy is the torsion shear stress is the moment divided by the polar moment of inertia into the radius. So from that equation we can get the torsion shear stress. Now to find the load in x and y direction and xy direction, we have to multiply the stresses with the thickness. As thickness is already given in the question, so we will find nx, ny and nxy. So now we got the A matrix, we got the nx, ny and nxy values. So from that we can get the mid-plane strains from this equation. As there is no curvature, it is symmetric. So the mid-plane strain will be equal to the global strain, and that is what they asked in the question to find the global strain x, global axis strains of the 0-degree plies. Now in next question they are asking the material axis strains in the 90-degree ply. So we already found here the global axis strains. Now we have to convert it into material axis strains. This can be done by using the transforming matrix and also the angle for which it is we have to find, that is 90-degree ply. So we have to put the multiply the global axis strains to the transforming matrix at 90-degree, and from that we can get the material axis strains in the 90-degree plies. The last question is the reduced transform stiffening matrix for the graphite epoxy plies are given. Now for a composite drive shaft, TB value formula is given where each symbol have their own significant meaning. Now a hollow composite shaft of 1.48 meter length is made of 0, 45, minus 45, 90 symmetric laminate having 0.25 mm thick plies and with its outer radius of 50 mm. Considering a factor of safety equal to 3, if the shaft needs to transmit a torque of 80 Newton meter, then the shaft will be, and the options are given. So for a shaft, here we have to consider its buckling. For that, as there is a torque given to it, there is a moment. So here we will consider the D matrix. So first we have to find the D matrix. As we already know the equation for D matrix, we need the reduced transverse stiffness matrices and the thickness of each ply. And from that we can find the D matrix. And the B matrix will be 0 here as it is symmetric. So from that we can get the values of Ex and Ey from this formula. Now putting the value of Ex and Ey in the formula given in the question of TB, where Rm is the mean radius that you can find here. Putting all these values, we will get the TB value. Now they gave us the factor of safety as 3. That is the shaft, the torque that can be transmitted by the shaft should be multiplied by 3, and that will be the value with, and the torque which it is giving should be more than the value of 3 times the torque that needs to be transmitted by the shaft. So whatever value of the TB we are getting here by putting all the values, it should be more than 3 times of 800 Newton meter. So after calculating here, we can see that it is more than 800 into 3 times of 800, which concludes that this shaft is safe and it is exceeding the safety, the factor of safety. Hence, here there will be no buckling. So the option will be not buckle, as the critical torsional buckling torque is more than the design torque. Okay. So basically in this question, critical torsion buckling torque formula is given. We have to put values in that formula, and the design torque will be what torque is given in the question, and considering the factor of safety, we will multiply the given design torque, and then whatever torque we are getting should be more than the one by the more than the design torque, then there will be no buckling. Okay, any doubts?
No, madam. No, madam. Thank you.
Have you
It's a clear.
started doing the assignment? 10.
Yes, madam. So after this, I can solve remaining also.
Okay. Okay, then if you have no doubt, then we will end the session here. Thank you.